Record. Okay. Cool. All right. So get these 2 tests back, 3 tests back. Noise down there. Weird. Okay, so everyone has their test back. Great. So I'd say a really good test. It was your first pass at hypothesis testing and all that fun stuff. So I was gentle with the marking, and the bonus question helped. But overall, I'm really happy with where you guys are at. And so I'd say it was a successful test overall. We can look at the stats. I posted a little blurb, but we do have a lot to cover today. So we'll see if we get into it maybe in a little bit. So you'll notice that assignment 4 just has a little check mark. That's just because you all got 100% if you handed it in. It was the exact same as the test, right? So I was going to mark the test, so then why would I mark the assignment? So for some people, or for some reason, I should say, oops, people get upset by that, but I don't understand, because you probably wouldn't have gotten 100 if I'd marked it. So just take the 100% on the assignment and be happy about it. Okay, let me just find these last couple ones. All right. So assignment 4 was basically just handed it in. Nice work. So today, oh, does anyone need tables? Because we're going to use the tables again today, of course. So just borrowing tables for the day. Oh, that's because that's what you got originally. And then we took one. Yeah. Okay, cool. So today we're going to attempt to get through both 5.2 and 5.3. The reason I'm smushing them together is they're both for 2 samples, right? So far we've only talked about one sample, right? What's the mean of this sample? How does it compare to some number, right? Usually we're going to be more interested in, okay, we've collected these 2 samples. How do they compare? Right? How we've collected those are going to dictate how we do our analyses. So far, we have only seen one sample, right? So we have only analyzed the mean of one sample. And you know what? I was really pleased with how you guys were doing on the test. And I don't care if you're just memorizing this stuff and kind of just spitting it out, because eventually it will start to make sense. And so when I did my first stats course, it actually, no, I'm not ashamed to say it. It wasn't until I was studying for the final that I was like, oh, okay. So I was just memorizing and just kind of getting it out there on the test. But it wasn't until I was actually studying for the final, when I'd seen everything and just kind of, I guess, memorized it enough, that I was like, oh, okay, I get it now. Right. So I'm not expecting you to have a complete grasp on it, but the way that you put stuff down on paper looks good to me. Okay. So just keep at it. All right. I did leave quite a few notes on your tests, so make sure you read those. Right. Learn from those. Okay. And if you have any questions about the test, then just ask me later. Okay. So far we've only considered how does the mean of one sample compare to some number. Right. So usually, or I'll just say, how does the mean of one sample compare to some hypothesized mean? Right, that's what we have been doing. Usually we'll be more interested in how two samples are related. Right? So usually we will be more interested in how two samples are related. To complicate things, there are two ways that we could have two samples. Remember, two samples just means that we have two columns in our data set, right? So far, we've just had one column, right? One sample, right? So think about your test scores, right? Your test scores for test 2, that's one sample, right? So then there are two ways that we could have collected two samples. So the first way is if I were to compare your test 1 score to your test 2 score, right? For each individual, now I have two observations for each individual, right? So we have to know how to deal with that. We call that a matched pairs situation, right? Because each individual has a pair of observations, okay? So that's our first situation. The second situation is if we have two samples, say the scores for version 1 of test 2 and version 2 of test 2, right? Now there's no way to say, oh, well, this score matches this score, right? So now you have two independent samples, right? So we need to know how to deal with that. So how we've collected our data, will determine how we should analyze it. So there are two ways to collect two samples. The first one is what we call matched pairs or paired data, if you prefer. This is when we've made two observations on the same individual. Made two observations on the same individual. So for us, right? So for example, your test 1 score versus your test 2 score. We might want to know, was there an improvement? Was there an improvement? Some other common situations are before and after studies. Right? So other examples. Before and after studies. That one's really common. I don't know. They can basically be boiled down to before and after, all of them, right? But as long as you keep in mind that, okay, if you've made two observations on the same individual, then you have matched pairs. Okay. So what we do, just focusing on the matched pairs for a sec, right, is that, okay, so we want to try to capture how each individual has changed, right? So to do that, we actually just calculate a column of differences. Right? So we take your test 1 score minus your test 2 score, or if you want to, test 2 minus test 1, it doesn't matter, right? As long as you're consistent for all the scores, right? So then you calculate a new column of differences, and then you just look at that, and now you're back to a 1 sample test, right? A 1 sample test of the differences. Right? So to analyze matched pairs, we want to capture changes within each individual. Within each individual. So we calculate the difference for each row. Each individual has a row. Then we have 1 sample of differences. So then we can just use the 1 sample procedure, right? Just keeping in mind that we're talking about the differences. So then we can apply the 1 sample procedures to test if the mean difference, or I should say how, to test how the mean difference compares to 0. A difference of 0 means there's no change, right? And depending on how you've calculated your differences, right? A negative difference means something, either an improvement or I don't know, a drop in your test score. If we did test 1 minus test 2, right, a negative score. So if we calculated the difference as test 1 minus test 2, right, a difference equal to 0 means that test 1 equals test 2. A difference less than 0, right? So a negative difference must mean that test 2 had a higher score than test 1. Right? Means that test 1 is less than test 2. What if you have a positive difference in this case? The difference is greater than 0. Then test 1 must be greater than test 2. Right? Your test 1 score was higher than your test 2 score. So these differences tell you what happened for each individual, right? Did they get the exact same grade? Probably not, right? But did they increase or decrease from test 1? And so now that we're thinking about these differences, right, that's the only really new thing that we have to think about. And what's nice about matched pairs is that, remember before, right, for one sample, how does the mean of one sample compare to some hypothesized mean? So we had to figure out what that number was. For matched pairs, we're always talking about how does the difference compare to 0, right? So for matched pairs, we always want to know how the mean of the differences compares to 0. So what we have is, for matched pairs, or therefore, our H naught will always be our null hypothesis is that the mu of the differences, so we put a little subscript diff, right, because this isn't just any mu, this is the mean of the differences, and that's how we indicate that we know we have a matched pairs situation, right, is equal to 0. So if you look at your formula sheet, right, you have H naught is that the mu diff equals 0. And then for us, because I'm nice that way, our alternative hypothesis will always be that the mu diff does not equal to 0. Okay. The reason that I'm not going to talk about mu diff less than 0 or greater than 0 is because it's hard to kind of extract that, right? if test 1 has to be greater than test 2, first of all, it depends on how you calculated your differences, right? I said as long as you're consistent, you could have done test 2 minus test 1, right? And that would change what's going on here, right? It would reverse it. And so for matched pairs, I will always just give you a two-sided test, right? Just because it's hard to figure out these things, right? And how they translate to the two different samples. Okay? And so we'll always just want to know, is there a difference between these two groups? And you'll see in the example that we're about to do how it's a little bit clunky to try to do two-sided tests, but because we'll usually want to test one side, right? Is this one greater than this one? Is this one less than this one? Right. So we will only consider two-sided tests for matched pairs. So once you've decided, right, because now we've got two different question types that we've talked about, right? One sample mean or matched pairs. And so you're gonna have to read your questions and figure out, okay, what do I have here? If you've decided that you have matched pairs, that's great, right? Because if you have matched pairs, then you know that your null and alternative hypothesis are exactly on your formula sheet, right? For the one sample mean, you had to change out your mu naught for some value from the question, right? It's hard to figure out what that value is, right? So now, for matched pairs, it's a little bit easier, right? Even though we have two samples instead of just one. Okay? So this will always be your null and alternative hypothesis for matched pairs. Just making sure that you keep that mu diff on there, the subscript diff everywhere. Okay? But to test the hypothesis, oops, use T equals X bar sub diff, technically minus 0, we'll talk about that, over the square root, oh, sorry, I'm jumping ahead, over S diff over the square root of N diff. I jumped to two samples. This should look familiar, right? So remember, before we just had T is X bar minus mu sub 0 over S over root N. We always do our testing, right, assuming that the null hypothesis is true, right? So these are the same, right? Except that I'm just highlighting that all of these, right, X bar of the differences, right? Because once you have your column of differences, you can calculate the mean, the standard deviation, the sample size. So the X bar of the differences, that's the sample mean of the differences, minus 0, because our null hypothesis is that mu diff equals 0. Right? And so it'll always just be 0, and that's why it's 0 on your formula sheet. And then the standard deviation of the differences over the square root of the differences, or the number of differences. We always do our testing assuming that H naught is true. Right, and in this case, we said H naught is that mu diff equals 0. And so that value will always be 0. Once you've found your T, right, you need to use the T table, but then we need our degrees of freedom. On your formula sheet, right, you have the degrees of freedom is just n diff minus 1. So matched pairs is really nothing new, right? It's just this idea that in the beginning, okay, we've collected 2 observations on each individual, and then we need to find the differences, right? But on the test, I'll have given you the differences, or I'll give you at least the mean of the differences and the standard deviation of the differences and the number of the differences, right? Which is really all you need to do the test. So we'll parking lot that for just a second, because I want to talk about 2 sample means, right? How are they different? Let's see here. No. Okay. How did I start it here? All right. 2 sample means. This is, I'd say, the most common situation, right? If you want to compare males and females, right? You want to compare Kelowna to Penticton. You want to compare BC to Alberta. You get the idea, right? So there's no natural way to match one observation to the other, right? Then we have 2 independent samples. So 2 sample means is when we have 2 independent samples and want to compare their means. What's really cool is they don't even have to have the same sample size, right? You could look at comparing the heights of 15 females to the heights of 20 males, and that's okay, right? Because these are 2 independent samples. And so our 2 independent samples can even have different sample sizes. How we analyze these, right, is that now there's no way around it, right? We've got group 1, group 2, right? Version 1, version 2 for our test 2, for example, right? I think there were 18 of you writing version 1, 19 in version 2 or something like that, right? Different sample sizes, right? Each of the groups is going to have its own mean, its own standard deviation, right? And so now that we have these 2 groups and there's no way to match them up, right? We have to deal with 2 sample sizes, 2 sample means, and 2 sample standard deviations. Okay. So with two independent samples, we must consider x1 bar and x2 bar, right? Sample means of each. I would have said group if I had more room. Ran out. Right. S1 and S2 sample standard deviation of each. N1 and N2 sample sizes of each. Right. So we've got a lot more information here. So that could come in the form of a blurb, right? Or in a table form. Might be given in a blurb or in table form. Group 1, group 2. X bar, S, and N, for example. Where I give you X1 bar, X2 bar, S1, N1, S2, N2. Right, so we have to keep those little subscripts on just to keep track of which group is which. Again, it doesn't matter which group is assigned group 1 and which one's assigned to group 2, as long as we're consistent. It doesn't matter which is group 1 or 2, as long as we're consistent. So we want to compare, how does the mean of group 1 compare to the mean of group 2? Right? So we want to know how the mean of group 1 compares to the mean of group 2. So for our null hypothesis, what we do is we say that our null hypothesis is that mu1 equals mu2. We have to assume that they're the same until we have proof otherwise. Right? Or if you want to, you could say that the null hypothesis is that mu1 minus mu2 equals 0. If you want to, you'll notice on the formula sheet that I have this way. I don't actually, well, I guess I write a little bit less is all. Right? I also find that it's easier to think in terms of, okay, mu1 is equal to mu2, or mu1 is less than mu2, mu1 is greater than mu2, right? So I just like to have the two of them to compare instead of, again, how does the difference in the means compare to 0, right? So notice that this is the difference of two means, whereas matched pairs was the mean of the differences. each. Right? So here, we're talking about the difference of two means versus matched pairs, where we talked about the mean of the differences. That's something to keep in mind. And I've put that on your formula sheet, right? Matched pairs is the mean of the differences that you're analyzing. How does it compare to 0? Whereas now we're talking about the difference in two means. And so your alternative hypothesis is going to be that mu1 does not equal mu2 by default. But here, right, unlike the matched pairs where I told you it'll always just be not equal to, here we could just talk about less than or greater than, but could have HA. Mu1 is less than mu2, or HA. Mu1 is greater than mu2, right? One-sided tests. So now we're talking about how does the mean of one group compare to the mean of the other group. So if you have a glance at your formula sheet, gets a little messy down there in 5.3, right? Which is the two sample means, but that's only because we have all this information that we need to cram in there, right? And so for our test, we calculate T is x1 bar minus x2 bar, technically minus mu1 minus mu2. That's not on your formula sheet, right? It's equal to 0, since we assume H naught is true. H naught says that mu1 is equal to mu2, or mu1 minus mu2 is 0, right? They're the same thing. No, that's standard. Yeah. So then we've got over this huge square root, over the square root of s1 squared over n1 plus s2 squared over n2. It's really important that you don't forget those squares. It behaves a little bit differently than before, right? Before we had s over root n, right? But if you think about just s squared over n all square rooted, that's the same as the square root of s squared over the square root of n, which is just s over root n. So they're a little bit different, right? Just because we're adding under here as well, but it's not that big of a stretch, okay? We can't pull the square root inside just because we're adding inside, but you can see the similarities of how we went from s over root n to s squared over n all underneath the square root. Don't worry about that. That's the formula, just know how to use it, right? But don't forget that square. In fact, I'll even erase this little tangent, but that's where it came from. Whee! So it's still very similar, right? Just had to be a little bit bigger to accommodate information from both samples. Right? Once you've calculated that though, right, and this is where you'll definitely want to know your store function on your calculator, right? Just so you can keep some values for later, so you don't have to keep plugging them in, right? And so we'll kind of get better at using our calculator if nothing else. Once you've calculated your t, we need to find our p-value, we need our degrees of freedom, right? Our degrees of freedom is going to be the minimum of n1 minus 1 or n2 minus 1. This essentially says take the smallest sample size minus 1. Smallest sample size minus 1. Remember, our degrees of freedom's been our sample size minus 1. Okay. There are way more complicated ways of finding the actual degrees of freedom, right? But this is a conservative estimate, and it works just fine for us. Okay. So this is a conservative estimate. We use when calculating by hand. Technically, we should, where did it go? Could use this little guy, but why? So you could go ahead and just calculate that. That's no biggie. We can. We're all capable, right? S1 squared over N1 plus S2 squared over N2, all squared, all over 1. But who cares? Okay. We're just going to use the smallest sample size minus 1 as our degrees of freedom. But when we do these calculations in R is going to do this. Obviously, it's a computer. Okay. And so you'll have slightly different degrees of freedom, and their degrees of freedom will be quite a bit higher than ours, right? But like I said, we're just using this very conservative estimate of the smallest sample size minus 1. Okay. R, I'll just make a note of this here. R will use this. And that's just to show you that saving you a little bit of work, right, just by taking the smallest sample size minus 1. Okay. Probably the notation that you're maybe not familiar with is the minimum notation, right? It just gives a list of 2 numbers. We take the minimum of those, and that's the one that we use, right? But besides that, nothing crazy. Okay. Of course, we can calculate confidence intervals for each of these, right? Matched pairs and 2 sample means. If you have a look, they take the same shape as they did before. I noticed on your test, everyone's feeling pretty good with the confidence intervals, I think. Right? For some reason, they just click a little bit better than hypothesis testing, and I'm happy about that. So I kind of leave the confidence intervals because you guys are already pretty good at confidence intervals, but we'll do examples of them in about a minute. How about that? Okay. So those are our 2 types of tests, right? The new 2 types of tests for 2 samples, the means of 2 samples, okay? And why haven't I talked about finding the p-value? Because it's going to be the exact same as before, right? At the end of all this, you've got a t in your degrees of freedom. Right? So to find your p-value, you do the exact same thing that you have been doing. Right? And then once you have your p-value, your conclusion takes the same shape. Right? If the p is less than the alpha level, you have enough evidence to reject H naught. And what does that mean in terms of the question? Right? So for both matched pairs, and two sample means, we have calculated a t in our test and found our degrees of freedom. So to find our p-value, we follow the same procedure as we did, oops, for one sample means. Once we have our p-value, how we draw our conclusions stay the same. That's nice, right? It's probably not your favorite part of hypothesis testing quite yet, right? But knowing that we're going to use the same procedure over and over and over again is pretty helpful, right? So even though if it doesn't feel good yet, it will be pretty good. All right. So I'm just gonna do, let's do an example. Oh, any questions before we do? No. Feeling railroaded? What happened? It's Monday morning. I know, right? So this is a kind of a too long intro to the question. You can probably think of something shorter, but let's do a matched pairs example. Okay. So I stole this from a textbook. So insurance adjusters are concerned about the high estimates they're receiving from Jocko's Garage. Jocko, that just sounds suspicious anyways. To see if the estimates are unreasonably high, right? So we have the suspicion that Jocko's estimates are higher than they should be. Right? Each of 10 damaged cars was taken to Jocko's and to a trusted garage, and the estimates were recorded. Is there a significant difference between the quotes from the two garages? So here is where I said, well, the two-sided test, right, gets a little clunky, right? Because I have to ask, is there a significant difference between these two garages, right? Garage 1, is it different from garage 2? And so, or is estimate 1 different from estimate 2? We would probably want to test something like, are Jocko's estimates higher than the trusted garage, right? Just reading this question, that's what we want to test, right? But in order to make sure that you have this not equal to in your alternative hypothesis, right? That's why I have to ask, is there just a significant difference between these two garages? Okay. And so let's have a look at our data here. So here's the data that we've collected. So each of these cars, right, there's 10 cars. Each of them has some amount of damage, right? They don't necessarily have the same amount of damage, but that's okay, right? Because this one has just a little bit of damage. It looks like the quotes are about the same, right? They're in the lower end. Here we've got a car with more damage, right? But because we're looking at across this car, right, we've got these matched pairs. And so when we calculate the differences in the quotes, right, what we're going to do is we're going to calculate the column of differences. And then that'll capture, right, the change between each of these quotes. Right? And that's why we don't want to just look at Jocko's estimates versus the other estimates, right? Because they are actually linked. And we want to capture that change from Jocko's estimate to the other estimate. And so this is a matched pairs situation. Doesn't matter because for that, we can calculate the mean and the standard deviation of each of these groups, right? As soon as we have a sample, we can calculate the mean and the standard deviation. They'll have some sample size, right? But in order to properly analyze this, we have to treat it as matched pairs. So, to properly analyze this, data, we need to treat it as matched pairs since we are making two observations on each car. Since we are making two observations on each car. So step one is we would calculate the differences. Now, I'm not going to get you to calculate the differences. I'll just give you the differences and the mean of the differences and the standard deviation of the differences. Okay. I'll just steal them here. Save some time. So all you really need from this here. So here we've got the differences. Let's think about what a positive difference means. A positive difference means that Jocko's estimates are higher than the other estimates. Good. But a negative estimate, right, tells us that Jocko's estimate was actually a little bit lower than the other garage. Right? So now we have this new column of differences, and we can calculate the mean and the standard deviation of those differences. And what's our sample size of the differences? We have 10 differences. Right? And so notice, right, that we can just, pretty sure if we just subtract across, because this throws people for a loop sometimes. If you do 1216 minus 1136, that is 80, right? But if you do 550, I'll skip the decimals, minus 521, that's 29 and not 84.59. So we can't actually just subtract across. It works for the means, but that's only because of how means are calculated. Remember, the standard deviation has sums and square roots in there. So it actually doesn't translate to just subtracting across. So that's why I have to give you the standard deviation of the differences. Okay. So notice, oops. Notice that S of the differences is not the same as S of Jocko's minus S of the other garage. Right. And that's just because the standard deviation, right, is telling us the spread of the differences. So here, this is equal to our X bar of the differences, and this is equal to our S of the differences. And our N of the differences must be 10. We want to know, is there a significant difference in the quotes from the two garages? So that's what we want to know. It gets a little wordy, right? Because we want to know if there's a difference between the quotes. And so to do that, we analyze the mean of the differences, right? But it's all contextual. So we have to keep track of all these differences. Okay. So we start with our null hypothesis. We're feeling good because we've got a matched pairs on our hands. And I'm pretty sure if I was writing the final, I'd probably just start by finding the matched pairs question, get that one out of the way, because I know for sure that I know my null and alternative hypotheses kind of gets me off to a good start, right? And so my null hypothesis is always going to be mu diff equals 0. Our alternative hypothesis is that mu diff does not equal to 0. Right? And the reason for that is because we want to know if there's a significant difference making this a two-sided test. Nice. Because it turns out we don't care which one's higher, which one's lower. We do, but I don't want to add that extra element. And so we just want to know, is there a difference between these two groups? So this was step 1, I guess. Step 2, do the test. Oops. This is where we calculate T is X bar of the differences. And I want to see these little subscript differences minus 0 over S diff over the square root of N diff. You're always showing off that you know you have matched pairs. X bar of the differences was 80. 80 minus 0, I'll just start dropping the -0. It doesn't matter. 80 over 84.59052. 84.59052 over the square root of 10. I've got it, Martha Stewarted. Ready to pull out of the oven. 2.990668609. I'll just leave it as that. I'll round it in finding the p-value. So step 3, find the p-value. Here, now we're back into somewhat familiar territory, right? Once we have to find our p-value, then everything kind of stays the same, because now it doesn't matter how you got this t behaves the same way that the other t was behaving, right? And so we say, using the t-table, with degrees of freedom equal to n diff minus 1, which is 10 minus 1 equal to 9 now. We find that the absolute value of t equal to 2.991, I guess. Remember, we have to have at least 3 decimal places for t, even if it's 0. I was making little notes on your test. If you decided to not write the 0, I still want to see that 0, right? Because 0 is different from nothing. What is? So we've got 9 degrees of freedom. And so we're trying to place our 2.991. We're getting pretty good at this now. So it's between 2.821 and 3.250. So we need a 2-sided p-value, right? Because we have a 2-sided test. So I'll start with saying, okay, now my 2-sided p-value, or my 2-sided p, must be between, and I just scroll down to the bottom, the very bottom this time, is between 0.01 and 0.02. One thing to remember, because on the test, right, I made sure that your alpha level was on the cusp of these, right? So depending on which version, it was either down here or down here, right? Your p-value is somewhere between 0.01 and 0.02, right? So that's important to keep in mind. There's only one value for the p-value. It's somewhere in between here, right? So if your alpha level is 0.02, for example, then your p-value is less than that. If your alpha level is 0.01, then your p-value is greater than that, right? Because it's between these two values. So that's something to keep in mind, something that I saw on the test. Okay. For us, I don't think we were given an alpha level, so we use the default alpha level of 0.05. Okay. So our step 4 is our conclusion. And we just use the same blurb that we have been using, more or less memorized. Since our 2-sided p-value, right, we want to show that we know what it is between 0.01 and 0.02. It is less than, right? Both those values are less than 0.05. So we can say that our p-value is less than 0.05. It is less than our, I'll say, assumed alpha level, only because we weren't given it. So we're saying, hey, I'm going to assume that it's 0.05, alpha level of 0.05, which means we have enough evidence to reject H0 in favor of HA. If we're going to reject something, we should probably say for what, right? In favor of HA. Okay. What does this mean in terms of our hypothesis? Right? It means that, yeah, mu diff is significantly different from 0. Right? A difference of $80 on average, right, is significantly different from 0. Remember, even though you might think, oh, 80, that's different from 0, we have to take into account the standard deviation, right, that spread. And that's what the t does for us, right? So therefore, there is a significant difference in the quotes from the two garages. Right. So therefore, there is a difference, or I'll say a significant difference, between the quotes of the two garages. That's all we can really say with the test that we did. Right. We would have to do another test, but really we can probably just say that Jocko's estimates are higher. Right. You'd have to do it with a one-sided p, right, but it's even smaller. So, but this is all we can say with certainty. We can add, though, we suspect Jocko's estimates are higher than the other garage. So what if we had to use a confidence interval? So test the hypothesis using a, what should we do here? 95% confidence interval. Default is an alpha level of 0.05 and a confidence interval of 95%. That's just default. But I'll always give you what confidence level I want, so it doesn't really apply as much. So what if we had to find our confidence interval? If we look at our formula sheet, our confidence interval looks like x bar of the differences plus minus t star. We find that t star the exact same way that we did for one sample. So it's the same, times the s of the differences over the square root of n of the differences. We have all these things. And so we need to find t star, right? So, same idea as before. So using table C with degrees of freedom equal to n diff minus 1, which is 10 minus 1, which is 9. And a confidence level of 95%, we find T star is, let's see, 95% going down to 9 degrees of freedom, 2.262. So now we can fill in x bar of the differences. I'll just rewrite it down here. T star S diff over the square root of n diff. We have 80 plus minus 2.262 times, oh, it was that big nasty, wasn't it? 84.59052. 84.59052, yeah. We're the square root of 10. So here, so 84.59052 divided by 10 square rooted. Just so you can check your values, 2.262 times 26.7498717. So times 2.262, so we get 80 plus minus 60.508208858. You're going to want to store that somewhere, right? And like I said, if you don't know how to use the store function on your calculator, I'm happy to show you. All calculators are basically the same, so we can figure it out. But store, I'm going to store it in 1. And then do 80 minus, recall 1, to get 19.49179142 up to 80 plus recall 1 up to $140.5082086. Now, because this is money, in my interpretation, I'll round to 2 decimal places. But as long as you go to at least 2 or 3, if you forgot you have monies here, that's fine. So what does this mean? It means that we're only 95% confident in this estimate, right? So we are 95% confident that the interval, and this is the same blurb as before, right? The interval from $19.49 to $140.51 captures the true mean difference in the estimates. That's important. We're talking about the mean of the differences. Right. So because of how we calculated the differences, they're both positive, right? So since both of these are over 0, right? Jocko charges between, we're 95% confident that he charges between $19.49 and $140.51 more than the other garage on average. Since both these bounds are over 0, we can reject the null hypothesis that mu diff equals 0. That's a nasty mu. Nice.
Why didn't we get to the alpha level though? Like, if we use the 95% confidence level, then found the degrees of freedom.
Yeah.
Which found our 2.362. But I don't understand where the alpha level is.
So the alpha level is for your hypothesis testing, right? Your confidence level is for your confidence interval. So they're different. Sort of.
Yeah, I don't know why. Like, I understand for the other question why we would need to have the alpha level for like when you're determining the p-value and 1 and 2 kind of thing.
Yeah.
I don't understand why.
Oh, well, they match up. It's just because the central 95%, right? You've got 2.5% here and 2.5% here. This makes a two-sided alpha of 0.05. Things got messy down there. See ya. Oh, if you didn't get your test back, come grab it.